Hi again. This is Mr. Nichols, and today I'd like to talk a little bit about what's called the root mean square error when you curve fit a set of data. So what I want to start with is go to the graphical analysis application on the iPad, and I'm going to look at a data set that we've already tried to work on in class, which is a basketball player's points per game on average versus their salary. So this is a data set that we had kicking around. And what I've already done is I've already fit it with a quadratic. But if we didn't know what kind of fit to put on this, this is the way the data layout. And notice that the window doesn't go to 0. This application always fits the data to the window or vice versa. So it goes to the lowest XY ordered pair and to the highest. It always frames it. But you always have the ability to rescale the axes if you want to see more detail, as in, say, zooming farther out. Let's just say we're working with this, and let's go with the simplest fit possible, which is the linear fit. And I'm going to hit apply, which means it's going to actually make the fit and do the calculations. You get an information box on the right-hand side, and it tells you that this linear fit is of the form y equals mx plus b, where m is the slope and b is the y-intercept. And it gives you the value for slope, y-intercept. There's r, which is called a correlation coefficient. We're going to focus on what's called the RMSE, the root mean square error. And I'm going to do that today. If we look at that number, it's fairly large, and you want to be careful about thinking that a large number is not a good indicator. When you look at this, you look at the fact that the data points are not all hitting the line. There are some that are closer than others. The root mean square error is a statistical measurement of how far in the y direction the line is separated from a data point. So every time there's a data point here, if you look at the vertical spacing or the gap between that point and the line, if you average all those together, that is the root mean square error, or that's how I'm thinking about it. The larger the number, the more aggressive the spacing between the line and the y values. The smaller the number, the closer the spacing. But within a data set, the function that has the lowest RMSE fits the data the best, but it doesn't necessarily mean that is the most appropriate function given what you're mapping out. So it may do something unpredictable, it may fit really well, but it may not make sense physically. Let me show you what I mean by that. The linear fit gives us an RMSE of 138,100. And what that technically means is, on average, this line is off on the salary estimates by $138,100 at every point on the line. Considering we're looking at a data set that goes up to about 1.6 million, that's still a fairly hefty percentage of it, at least 10% on the high end, even more on the low end. Let's try another fit. Or what I like to do to kind of figure out what's going on is you can actually reset the axes. You can pinch on them to make the values more comprehensive, and it gives you a bigger picture of what's actually going on in the data set. And you can see that that last point, that jump to 1.6 million, really does stick out for just a couple of more increases in points per game. But still, to me, it looks fairly linear. But again, if you squash the y-axis too much, you can make anything look linear. Let's take a look at another fit. So let's kind of go down the list here. And let me go to the next one, which will be a quadratic. So kind of like y equals x squared, or ax squared plus bx plus c. So the quadratic fit has the form of a quadratic equation. So it's going to carry that ax squared plus bx plus c. So it's going to have a squared term, a linear term, and a constant value. So you are going to have a y-intercept, which is actually the c term, a linear term, which is the b times x, and then the quadratic, or the power of 2 term. If you look at this one, look at the RMSE. It's 87,110. It's almost cut the RMSE gap in half. So it says, hey, this is a better line fit. But you also have to look at this and say, does the line or the curve make sense if you look to the left and the right of the data set. If you go a little less than the points per game that we mapped out and a little more, does it seem realistic? That's something we need to look at. So what I want to do is I'm going to pull these down here a little bit and take a look at this. If I continue to map this out a little bit and look at what happens, if you look at the quadratic function, there's something going on there where if you look really aggressively here, you can see a point where the curve is actually going back up. So it's almost like at 0 points per game, you make more than you would at, say, 1.5, 2 points per game. Now, so it's a slight curve down, then it goes back up. Now that probably doesn't make sense. But the other problem here, in terms of realism, is if we flip down and look at the linear function, look at that one. Okay, that says if you make 0 points per game, you owe the franchise, and if you look at the linear function, it says you owe the franchise $102,400. So obviously that's not realistic either, because even a player on an off year scoring, say, 1 or 2 points per game, while they may not last on the roster for long, they're still getting paid a hefty sum. So there's going to be a non-zero value there. So I'd say the linear probably isn't a very good fit compared to the quadratic in terms of the realism. It seems to fit better at the low values. It's a little closer, a little more realistic. Let me try another one. So we did quadratic. Power function, let's take a look at what that one tells us. So let's see, I got to apply that. So ax to the b. What I want you to notice about this one, I'll kind of hide these, is this is of the form ax to the b, and the power of b is 1.2, 1.3. So it's close to almost being a linear function. It's going to be slightly curved up. Again, that might be a good fit, but when you have 0 points per game, you have zero salary. And I think you could make the case that you're going to make something even if you're not making that many points per game. After that, you start getting into, say, inverse and inverse squared, and you can see the fact they're going the wrong way. They're just going, yeah, no. So if we zoom this up even more, again, pinch the axes, you can see what's going on here. I would probably make the contention that of the 3 fits here, of the big trials, that I would probably go with the quadratic. So I'm going to just kind of zoom back in here and look at the data and say that I realize the fact that it looks like the trend is somewhat linear. This is a case where the quadratic does speak to being a tighter fit, and the values look a little better as you go to the low end. And on the high end, it may be a little unrealistic to think it's going to go up much more than that as far as player salaries. But when you're evaluating these, there's going to be a little room for interpretation, but the real lesson here is don't take the RMSE as the absolute. It's something to look at, and you might have 2 or 3 or 4 fits that are around the same number. So if you had 87,000, 85,000, 78,000, 90,000, I'd still take those as close, because in the range of those numbers, they're still fairly close as far as percentages off each other. It really comes down to, if we look at those values, what seems to make the most sense in terms of the curve fit? Is it an accelerating curve fit? Salaries going up markedly per increase of point per game? Do you think it's going to plateau and go the other way? Is it possible to have a power function that goes like this and tails off? So those are things you want to think about as you're looking at this. But I would highly recommend not just leaving the window on the existing data points, but adjust them, change the scale. Remember, you can always go down to the bottom on the lower left icon for graphing, edit the graph options, put the left at 0, put the bottom range, put that at 0 also. So basically, so you're looking at the quadrant number 1 on a graph. It's going to show you what things happen as far as when you make 2.5 points per game and you get no money. Or does it make more sense to have some money at a low point value? I will contend that I think the quadratic is better in that zone. It may not be better on the high end, but they're all kind of trending through those last 2 points, which have a massive shift in them. So as you're looking at these, be versatile. Think about moving the scales around, play with the axes a little bit, see what seems to make the most sense. Because I'll probably ask you to do that and defend why you picked a particular fit. And if I like your argument and agree with your argument, you'll probably get the credit. If I don't agree with it, but you come up with some really solid rationale why you picked what you did, partial credit will be in store for you. So that's the end of this one. Have a good night.